about continuity, which is again something we've already talked about before, but I want to go back over. As you can see here, I've got the 3 different rules for continuity at a point. In order for a function to be continuous at a point, in this case we're calling it C, but it's any point. First of all, f of c has to be defined, so there has to be a defined point or a defined value. Limit as x approaches c of the function has to exist, so the limit must be the same from left and right. And then finally, those 2 things have to be equal to each other. So limit as x approaches c of f of x has to equal f of c. If those 3 things are true, then the function is continuous at that point. Another thing, just some more terminology, just as a reminder about the types of discontinuity. So in this case, we're talking about places where we are not continuous. We have 2 different types. Sorry about that. We had an announcement. Back to the 2 different types of discontinuities. We have removable and non-removable. Okay. Removable discontinuities, I've tried to put a little reminder for each of the different types you might see it. If we're talking about an equation, then this is something where you might have the factored expression where you can remove a factor out and still take the limit, which is another very important part about removable discontinuity. The limit still exists. If we're talking about a piecewise function, then the limit is still the same from left and right, but it's not equal to the value of the function. And then finally, for graphs, there could be a hole in the graph, so we're approaching the same value from left and right, but there's no defined point, or it's not the same defined point in the same value as the limit. For non-removable, as far as equations, then it's something where we cannot factor it to remove the expression, or if we're talking about, think about something on the bottom that we can't factor out, or if it's piecewise functions, then it may be approaching 2 different values from left and right. For graphs, there could be a jump in the graph, so we're not approaching the same value from left and right. We could be going to 2 different places from left and right, or there could be an asymptote. Anytime there's an asymptote, that's called a non-removable discontinuity, and the limit does not exist. All right. Again, that was just a review of some rules and terminology. Let's take a look at some examples. First, let's start with looking at graphs. For each graph, find any discontinuities and specify the type. So let's take a look at this first graph in part A. In part A, we can tell that there's only really one place that we have to worry about. Everything is pretty smooth, and we are continuous except at this x equals 1 value. Okay, so at x equals 1, we're not continuous. Let's talk about what type of discontinuity it is. If we approach from the left, we're approaching 4. If we approach from the right, we're approaching 0.5, it looks like, after I've graphed all over everything. So it looks like about 0.5. So we're definitely approaching different values. Since we're approaching 2 different values, the limit does not exist. And so this is going to be a non-removable. Okay. Also, a lot of times with discontinuity, we have to tell why something doesn't exist, or why something is not continuous. The reason that this function is not continuous at x equals 1, we do have a defined point. So the first condition is met, but the limit doesn't exist. So the reason that we're not continuous would be because the limit as x approaches 1 of the function does not exist. Okay. Let me change up color here. Let's look at the second graph. Okay, the second graph, it looks very continuous except for one place at x equals 5. Let's talk about at x equals 5. At x equals 5, we have a hole in the graph. Okay, so think about your conditions. F of 5 has to be defined. We have a defined point. It's here at 3. The limit as x approaches 5 has to exist. We are definitely approaching the same values from left and right. So the limit does exist. The limit is 1. The problem with continuity is that those are not equal to each other. Okay, the defined point is not equal to the limit value. So this function is not continuous at x equals 5. Now this one is what we call removable. Okay, because the limit still exists. It's just a hole in the graph. If we needed to write a reason why it's not continuous, remember we already said the function's defined at that point, the limit exists, but those are not equal to each other. So our reasoning for not being continuous would be because the limit as x approaches 5 of f of x does not equal f of 5. All right, so that was taking a look graphically. Now let's take a look algebraically. So A and B are pretty similar. They're both rational functions. Let's talk about what can happen here. Now, anytime you have a rational function, so you have the fraction, anything that's going to make the bottom equal to 0, you're going to have a discontinuity there. So we can already tell in part A, we're going to have a discontinuity at x equals -1. Okay. Now we have to figure out what type it is. Okay. We're undefined here. So again, if they needed a reason, because f of -1 is undefined. Okay. But let's talk about the type of discontinuity. So we want to see if we can factor and cancel this out. The top, if we tried to factor, would be x minus 2x plus 1. So we could cancel. So that means this is a removable discontinuity because we could remove that factor from the equation. Okay. And the limit would still exist. Let's look at that second one. If we set the bottom equal to 0, we know we're going to have discontinuities at positive and -3. That would make the bottom equal to 0. So we know we are not continuous there. Let's talk about what type. If we factor the bottom, that's a difference of squares, x plus 3, x minus 3. So the x minus 3's would cancel out. That means x equals 3 is removable discontinuity. That's just a hole in the graph. Whereas x equals -3, there's going to be an asymptote there. That is non-removable. Okay, and it's pretty easy to remember for rational functions which type, because can you remove the factor from the equation? Okay, then it's removable. Can you not remove it? Okay, it's non-removable. Take a look at the next two, though, because now we're looking at piecewise functions. For part C, we have a function for when x is less than 2, and then we have the value of 0 for when x is greater than or equal to 2. So the only place we really have to worry about this thing not being continuous is where it's broken up. So we're looking at 2, what happens at 2. So let's check the limit. We know we have a defined point, f of 2 is going to be 0, but let's take a look at the limits. Limit as x approaches 2 from the left, we would be looking at that top function, because that's when x is less than 2. If we plug in 2, 2 times 2 minus 10, 4 minus 10 gives us -6. Now let's look limit as x approaches 2 from the right. Okay, that's when x is greater than 2, so that's just 0. Notice those are not equal to each other. -6 is not equal to -6 is not equal to 0. So we know that we now have a discontinuity at x equals 2. The limit did not exist, so this one is non-removable. All right, let's take a look at that last one. A little bit more involved because we do have two places where this is broken up. We're broken up at 0 and we're broken up at 3. So let's check limits for 0. Limit as x approaches 0 from the left would be plugging into -x minus 3, so that's going to give us -3. Limit as x approaches 0 from the right is going to be using this equation when x is greater than 0, so that's going to give us -3. So we can tell all conditions are met. At negative or at 0, our function is continuous. We have a defined point of -3, and then our limit exists, and it is equal to -3, so we are continuous. But let's check 3. Limit as x approaches 3 from the left. Okay, we're going to plug into this middle equation for when x is less than 3. If we plug in 3 there, we have -9 plus 6 minus 9. So that's going to end up giving us what? Okay, so -9 plus 6 is -3, minus 3 is -6. Now, let's find limit as x approaches 3 from the right. We're going to plug into this equation for when x is greater than 3. So 2 times 3 is 6, minus 4 is 2. Notice that those two are not the same, so the limit does not exist. So this one is non-removable at x equals 3. Running out of room here. Okay, so we got non-removable at x equals 3. Let's also take a look at another type dealing with continuity that's very popular, especially now that you guys are in AP, is finding the value of a constant that would make a function continuous. We have that a lot. For part A, find the value of a that would make f of x equal to ax squared plus 3x minus 4 when x is less than 1, and 3 to the x plus 2 power when x is greater than or equal to 1, continuous for all real values of x. So what we want to think about here is we need to make this function continuous, so we need to make those conditions be true. We're going to have a defined value, okay? We're going to have a defined point for 1. It's going to be whatever we plug in here when we plug 1 into this function. So what we need to check is the limit has to exist and also equal the same thing. So we got to check, is the limit from the left and right equal to each other? That will make the value of a something that we can solve for to make this function continuous. So let's take a look. If we were to find the limit as x approaches 1 from the left, we'd be plugging into this top function. Let's plug in 1. That would give us a plus b minus 4. Now, we want that limit, which was the limit from the left, to equal the limit from the right. Limit from the right, we're going to plug in 3 to the x plus 1 power, or x plus 2 power, excuse me. So if we plug in 1, that's 3 cubed. So now, all we have left for a variable is a, so we can solve. 3 minus 4 is going to give us minus 1, so we have a minus 1 equals 3 to the third power is 27. Add 1 over, so a has to be 28, and that would make that function continuous. Okay, take a look at the second one here. Find the value of k that would make this function continuous for all real values of x. Okay, so we can tell we have a problem at -3. Look at that function on the top. This f of x is equal to this rational function as long as x is not equal to -3. And when x is equal to -3, we have a value of k. But we've got to figure out what that value of k is. So if we are solving for k, we want to make sure the limit is equal to the function value. We know the function value at -3 is going to be k. We need to know what the limit value is. Well, think about this. Everywhere except at -3, we use this function on the top for f of x. That means that if we were trying to find the limit as x approaches -3, we'd be using this function because the function would look like this rational function as we're approaching from left to right. So let's think about what we can do. We can't plug in -3 as it is because we get 0 over 0. So let's factor the top. That'd give us x plus 3, x minus 3. Bottom, still x plus 3. Notice that would cancel. So now we know we can plug in -3 to find out that the limit as x approaches -3 would be -3 minus 3, which is -6. Now, we have the limit. We know that the f of -3 is k. We want these two to be equal to each other in order for the function to be continuous here. So k has to be -6. Okay. Those look a little bit more difficult, and people usually think that they're harder than they actually are. Those are actually pretty easy because we only have to solve for one limit. We don't have to do left and right because it would be the same value. One more. Now notice this one's a little bit more involved because we have two variables. We want to find the values of a and b to make this function continuous. So take a look at what we've got. We're broken up at 1 and 4. We want to do the same thing. We want limit from left and right of 1 to be equal, and we want limit from left and right of 4 to be equal. So let's start with 1. Okay, so let's start looking at 1. We need the limit from the left and the right to be equal. So if we look from the left, we're plugging into x cubed plus a. If we plug in 1, that's 1 plus a. Now from the right, we want to plug in 1, which would be that middle equation when x is greater than 1. So we'd be plugging in 1 to 2x squared. That'd give us 2 plus bx would be plus b plus 3. Let's just simplify a little bit. A is, let's see, 2 plus 3 would be 5, and we're going to subtract 1, so plus 4. All right, let's check at x equals 4. If we plug in 4, we have 2 times 4 squared, so 2 times 16 is 32, plus b times x, so plus 4b, plus 3. That's the limit from the left of 4. Now limit from the right, we're looking at this bottom equation. Cosine of pi x over 4, so cosine of 4 pi over 4 is cosine of pi, which is -1, and then minus 4. So let's just do a little bit of cleaning up here. So we've got 32 minus 3, or no, plus 3, excuse me. So that's going to be 35 plus 4b is equal to negative 5. Subtract 35 over, 4b has to equal negative 40. So now we know that b equals negative 10. Let's solve for a. A is b plus 4. So if we do negative 10 plus 4, that's negative 6. So a is negative 6. So these two values would make that function continuous for all values of x, because that's where it's broken up. All right, guys, I hope this was a good refresher. These are a lot of the types of problems you're going to see with continuity. We're going to do a lot of practice just to make sure we still feel comfortable, and then we'll start taking a look at some AP style problems dealing with limits and continuity.